Hello and welcome back. In section 5.4, we were talking about taking the integral of a rate of change of some quantity, and we said that it gave us the total change in that quantity on some interval. All right, so we're going to be looking at that same kind of situation again in section 5.5. So if, for example, if I have C prime of Q, which is the marginal cost, if you remember that, it's the rate of change of the cost to produce items, and it's the cost given in dollars, and Q is the number of items. Okay, so if I'm going to look at the definite integral from 0 to 200 of C prime of Q, then basically that is saying we're taking the interval of the rate of change of the cost. So that will give us the total change in cost if we're increasing production from 0 items to 200 items. Okay, so how is the cost changing as we produce a number of items, 0 items, 1 items, 2 items? How is that cost changing? We know that we talked about accumulating area under the graph of the derivative function or the marginal cost function. So basically what it's saying is that this is the derivative, but to calculate this integral, it's saying we need the cost function itself, or we could use the cost function itself to evaluate that. We have not had the luxury of that because we've never known the function whose derivative was given here in our integrand. Okay, but if we knew the cost to produce 200 units, the total cost, minus the cost to produce 0 units, then we could figure out the change in cost for those two production levels. Okay, but we still don't know that cost function. That is more of what we will do in chapter 6. Okay, but let's talk about what these two stand for. So I know cost to produce 0 items, well, that's what we call our fixed cost, right? If you have some kind of a cost and you're producing nothing, that's your fixed costs. And we know that those are typically given to us, okay? This is the total cost to produce 200 items. And we know that if we have the marginal cost graph, then we can evaluate this definite integral. So what we're looking at here is if I can find this area calculated by this definite integral and someone gives me the fixed cost, then I could find the cost to produce 200 items. So we say then that, okay, the cost to produce, total cost to produce 200 items is C of 0, or the fixed costs, plus this definite integral here, which this is actually called the total variable costs. Okay, because if you think about it, the cost, this is telling me about the rate of change of cost per item. So at each production level, the cost is changing. So that's why we call it the variable cost. And we've talked about fixed cost and variable cost to make up the total cost. Okay, so that's the whole idea here, is if I can find the total cost for producing a certain number of items if I have two things. One of them is I need the marginal cost graph, because then I can find the total variable cost from it, and I need to know the fixed cost. So I need two things. All right, well, here's the graph of that marginal cost function we were just looking at. And because it is linear, we can find that area by dividing it up into a rectangle and a triangle, as we've been doing, and we can find the exact area this way. So this rectangle here has a height of 10 and a width of 200. So 10 times 200 is 2,000. So basically I have $2,000 in that region. Now, if I find the area of the triangle, this side is from 10 to 40 is 30. So I have 30 times 200 again, and then I take half of that. So in here, this area represents $3,000. So this definite integral here is going to be $5,000. So we're saying that is the total change, the total change in cost to go from producing 0 items to 200 items, or our total variable costs. So if we want to know the total cost to produce 200 items, then we're going to need our fixed costs and that total variable cost, which now we have. So the graph gave us that. Somebody had to have given us the fixed costs. So we can say basically then the total cost for producing 200 items is the fixed cost, which is $1,700, plus my total variable cost, which is $5,000. So the total cost to produce 200 items is $6,700. Okay. Now, if this looks familiar to you, we were doing something very similar to this in 5.4, where we were finding the change in total change in distance traveled, the displacement. Okay, and we said once we found that, we added it to some to our beginning amount or initial amount. That's like our fixed cost, something that we had to have been given. Okay, so let's summarize some things here. If C of Q is my marginal cost function, or remember sometimes we saw MC of Q for marginal cost, and C of 0 is the fixed cost, then we know the cost to increase production from A to B units is given by this definite integral. The total variable cost is this interval here from starting at 0 up to a certain level of production. And here's what we're really getting at, the total cost of producing B units. So we could say the total cost of B units is the fixed cost plus the total variable cost, which is that integral. Okay, so this is what you'll probably be using the most, or will be using the most. Okay, so let's look at an example. Here's our marginal cost function. We can see it's quadratic, and they're telling us fixed costs are $30,000. So I want to know what's the total cost to make 160 items. So I want to come up with C of 160. Okay, so I'm going to start with my fixed costs, $30,000, and I'm going to have to add on my total variable cost, which is basically that value of that definite integral. Okay, now, so what we find out then is that I don't have the graph for this marginal cost function. So the only way, and if it's not linear, if I notice it's not linear, so even if I have the graph, I can't calculate the exact area. I would have to approximate it with rectangles. So right now, all we can do is to find these definite integrals is we can find exact value if it's made up of linear components, or we can approximate it if it's based on a function that is a curve. So using rectangles. We will be able to exactly evaluate this definite integral when we get to chapter 6. So what are we going to do? Someone has to tell us how many rectangles. So if we're going to use 8 rectangles, then what's the width of each rectangle? Whoops, so I'm not using X now. My horizontal axis is in Q, or number of items. So delta Q is B minus A, 160 minus 0, divided into 8 equal rectangles. So that's basically 20. So the width of each of our rectangles is 20. So we would start at our first value A and then continue adding 20 to get our X values, which I've done already. We've done quite a few times. To get our heights or our function values, we just plug our Q values, those different quantities, into our function to get these function values or those marginal costs at each production level. Okay, so we're saying if we produce 20 items, then the marginal cost at 20 items is $99.20, meaning the cost to produce the 21st item is $99.20. Okay, so what we can do then is do our left-hand sum and our right-hand sum and then average those. So this is a review, so I'm going to kind of go through it fairly quickly. So the width of each rectangle is 20. We add up the heights. And remember, if we're doing the left, we use the first 7. Okay? And because of time, I'm not going to write them all down, but give you an idea of which ones you're adding up. So our last value, if we're doing a left hand, would be this one right here. So it'd be 60.8. Okay, so you'd add up those 8 numbers and multiply by 20, which comes out to be 11,520. Okay, so we're approximating that change in cost to be $11,520. Okay, so when I do the right hand sum, then once again rectangles are a width of 20. I then start with the second value in the table and then use those 8. So I'm going to start with 99.2 and then add those 8 values. So I will be using the last value, the 76.8 will be my last value. So add those up, multiply by 20, get our approximation is $10,496 for our total variable cost. So if I average those two together, that would give us our approximation for our total variable cost to be $11,008. Okay. So if I want, the idea here was to approximate the total cost of to produce 160 items. So it's going to be, we're going to have to take our fixed costs, which would be, we need our fixed, let me write this down, plus our variable cost, total variable cost. So our fixed cost, we said, was, what was it, $30,000. And the total variable cost, we just approximated that to be $11,008. So we're approximating the total cost to produce 160 items to be $41,008. Okay. Now, if I would have had the graph of the marginal cost function, I could have done approximating the areas under the graph. Okay. Or we could draw a graph with these points. We could put these points on our marginal cost graph and kind of approximate it that way, but extra work. But here's the graph, so let's take a peek at it. It's kind of cool. So we're basically saying then that our total variable costs would be this area here in green, would be the 11,008. Okay. Be that area. So the other thing then we could look at is we could find other total costs using those values. Okay, so for example, I could say, all right, let's talk about what is C prime of 60? What does that mean, C prime of 60? Well, it's the marginal cost at a production level of 160. Okay, I can get that from my graph, or better, I guess, from my table. And the table says the exact value from substituting in. If we're at a production level of 160 items, the marginal cost is $76.80. Okay, so C prime of 160 is $76.80. So that's a point on my marginal cost graph, which, okay, so what does that mean? Do you remember what marginal cost means? So we're at a production level of 160. Marginal cost is basically what's the rate, how is the cost to produce each item changing? Okay, well, it's changing at a rate of $76.80. So we would say that this is the cost to produce the 161st item. So remember, if we're at that level of production, that's what the next item will cost us, because that's the rate of change, cost per item at that level. Okay? So if I want to estimate C of 161, which is basically means total cost to produce 161 items. Okay, well, let's think about that. We know the total cost to produce 160 items. We just found that. Okay, so we can say C of 161, and we're approximating, would be the cost to produce 160 items, the total cost, plus then the cost to produce the 161st item, which is the marginal cost to produce one more. Okay, so I know this one, that's the one that we just found up here. Cost, total cost for 160 items is $41,008. And the cost to produce the 161st item is $76.80. So we're saying approximately the total cost to produce 161 items is $41,084.80. All right, so that's one of the things we are looking at in 5.5. But this whole idea of finding total change in cost by using the marginal cost function is an application of what we call the fundamental theorem of calculus. There's actually a fundamental theorem of algebra that every number can be written as a product of unique prime numbers. There's a fundamental theorem of algebra, which is, or did I say that? Arithmetic is the prime numbers. Algebra is every polynomial of degree n has n different complex or n complex solutions. You use it in algebra a lot. And then there's the fundamental theorem of calculus, which is fabulous, very useful. And that's what we will actually be able to use it to evaluate definite integrals in section 6.2, 6.3, I think. Okay, but look, it looks very familiar. It's saying if I'm taking the definite integral of a derivative, so this is, I'm integrating a derivative function on some interval. We know then that would give us the change in the function values. So it's saying, if I know the derivative function here, to evaluate this definite integral, I either need the graph, okay, and then I approximate, or if I can't actually calculate an exact area. But we could do it without the graph and not by approximating, by if we knew the original function. Okay, just like we said, the integral of marginal cost, the derivative of cost, if we use the cost function, we could find that value by plugging it in. Okay, so, but we've never known the actual function that we were integrating the derivative of. Okay, so I want to show you how this works with an example that we can figure out, so that you can see kind of another application of it, and then it's something to look forward to when we get to chapter 6. It opens our world up to so many possibilities and less work in terms of approximating definite integrals. So let's say I want the definite integral from 2 to 5 of 2x. Okay, well, I can actually get that, right, by doing some, by graphing it, because this function is linear, right? And I can actually calculate the area. So anytime you're trying to find the exact value of a definite integral with a linear function, graph it. So we're going from 2 to 5. So if I put 2 in, I get 4. This is not drawn to scale. If I put 5 in, I get 10. Okay, so I'm looking at my function, that line on this interval, and I want to calculate the exact area of that region. So if I divide it up, I've got a rectangle here, which has an area of 12, right? 3 by 4 is 12. And then I have a rectangle up here, or sorry, a triangle, hello, that is 3 wide, 10 high, so that's 30. Half of 30 is, wait, that's not 10, sorry. That's 6, and that's 3. 3 times 6 is 18. Half of 18 is 9. Okay, so I know this definite integral is 12 plus 9, which is 21. Okay, with the fundamental theorem of calculus, we don't need to do that. Okay, so we're saying that 2x is a derivative of some function. Can you think of a function that when I took its derivative, I get 2x? So you got to think backwards. Okay, and that's what chapter 6 is all about, going backwards. We know the derivative function. What was the function? Well, let's look at this. If I said x squared, what's the derivative of x squared? 2x. Okay, so we're saying then to find this definite integral, then we're going to take the function evaluated at the upper limit of integration minus the function evaluated at the lower limit of integration. So to find this, we would take f of 5 minus f of 2. So f of 5, 5 squared is 25. F of 2, 2 squared is 4. And we get 21. Voila. It's magic. Okay. Wonderful. So think about this. This is so nice. So this is really something to look forward to. So what we'll have to do is come up with, how do we go backwards? So just like when you learned rules to find derivatives, you're going to learn rules to find what we call antiderivatives, going backwards. Okay, so we can use this, we were using it in the last examples with marginal cost, an application of it. We can use this idea here of the fundamental theorem of calculus to help us find function values if we know something about the derivative. Okay, we still are not going to use it to evaluate. Okay, all right. So let's look at the graph. Here's a graph of a derivative function. How can that help us find ordered pairs on the graph of the original function? So here's the graph of the derivative. I want to know what are the points on the graph of the original function. Okay, I don't know the function. Okay, but the derivative tells us how the function is changing. Okay, and we can use this area or idea to help us. So let's take a look here. Let's say that I wanted you to find the definite integral from 0 to 6 of f prime of x dx. Okay, you're all experts at that. We've done that a lot. So it's basically the area bounded between the graph of that derivative function and the x-axis on the interval from, oops, I should have said 0 to 7, I guess. 6, 7, doesn't matter, 0 to 7. Okay, so find the area below. So this region here is 1 square. Okay, this is a half of a square. This is a half, so then we're above. This is 1, this is 1, this is a half, and this is a half below. Okay, so remember the definite integral then is area above minus the area below. So above we have 1, 2, 3. Below we have 1, 2. So I have 3 minus 2 gives me a definite integral of 1. Okay, we know how to do that. All right, so what if I said I want the definite integral from 0 to 1 of f prime of x dx. So the area bounded on just this interval here, basically from 0 to 1. Well, what's it going to be? We've got 1 square below, so it's going to be negative 1. Okay. Well, the fundamental theorem of calculus says, the definite integral from 0 to 1 of f prime of x dx is equal to the function value at 1 minus the function value at 0. Okay, well, I don't know the function, so I can't plug 1 and 0 in. But if I know one of these values, so think about f of 0 is kind of like my initial value. So if I'm given some initial value, which I've given a function value that I can use, the function value at 0. So this is f of 0. I do know that that is 2. Okay, so you have to be given that value, otherwise you can't do this. All right, and then I just found this is negative 1. So I know the two of those. I can find f of 1. I can find the function value at 1. So I add 2 to both sides, and I get negative 1 plus 2 is 1. Awesome. Okay, so if I knew the function, if I knew what it was, and I plugged 1 into that function, I would get 1. Okay, and so we could continue that process on. I could say, okay, I need to find f of 2. So I'm going to look at the definite integral from 1 to 2. I'll look at my next interval here of f prime of x dx. That would be the function value at 2 minus the function value at 1. Okay, well, this I can get from my picture, from my graph. The area between 1 and 2 is negative 1/2. Okay, f of 2 I don't know, that's what I'm trying to find. I know f of 1 though. F of 1 is 1, because I found that over here, so I can use it again. And find f of 2. Solve for f of 2. I'm going to add 1. Negative 1/2 plus 1 is 1/2. So f of 2 is 1/2. Okay, so a little convoluted, maybe. A lot of work. So, but that's the idea. We can use the fundamental theorem of calculus. Now, so basically what the fundamental theorem of calculus is doing is it is summing up the area as you move across. Okay, it's summing up the change. All right, so there's a much nicer way to do this if we understand that idea. Okay, we can find, here it is, we can find ordered pairs on the original function by using its derivative. And I will say this is like number 15 and 16 in your homework. I'm not sure what page that is. 267. Okay, and there are no examples of this in the book. So you want to use this example here. Okay, let me put my areas back in. I know this is 1, 1/2, 1/2 below, 1/2 above, 1, 1, 1/2. Okay, so as f prime of x picks up, picks up area, sorry, that's a typo, picks up area above the x-axis. So as we're going from 0 to 7, we're accumulating area. If it's above, then the function values are going to increase by that amount of area. Okay? When the area is below the x-axis, the function decreases by that amount of area. Okay, so here's my given starting value of 2. Okay, my function value. So if I'm going from 0 to 1, then what's happening? If I'm going from 0 to 1, then my area is negative, right? So I'm subtracting 1, basically. So 2 minus 1 is 1. So my function value at 1 is 1. Okay? So you're just keeping, you're applying the change in the area as you go across. So from 1 to 2, my area is decreasing by 1/2, so my function value will decrease by 1/2. So 1 minus 1/2 is 1/2. Okay, and continue on. So then when I go from 2 to 3, I've got a positive area, so I'm increasing it by 1/2. So I'm adding 1/2. 1/2 plus 1/2 is 1. Okay, so from 3 to 4, I'm adding 1, that's 2. From 4 to 5, I'm adding 1 to 2, I get 3. From 5 to 6, I'm adding 1/2, so I'm at 3 and a half, or 3.5. And then from 6 to 7, I'm decreasing it by 1/2, so I subtract 1/2, so at 7 I should be at 3. So if I knew the function, I could find those values, but I don't know the function, I can use the derivative. Okay, so if we want to do a quick little check, let's just make sure. Let's say that I want to do the definite integral from 4 to 5 of f prime of x dx. So that would be f of 5 minus f of 4. Okay. All right, so we know how to find this definite integral from the graph. So the area bounded by the derivative between 4 and 5. So that would be a 1. And f of 5, I don't know, but, well, actually, if we would have backed up the truck. So we have to know one of these. So if I said f of 4 was 2, so let's say I was going from here to here trying to find this. F of 4 is 2. I guess I should have stopped and done this earlier. Then I can find f of 5. So add 2, I get 3, which should be what I have in my table. And there you have it. Kind of fun. Neat little way of doing it. Hope that helps. See you soon.